Hello, and welcome to section 4.9. Suppose we know the derivative of a function. How do we get the function itself from that derivative? That's what antidifferentiation is doing for us. That's finding the antiderivative. So we're going to reverse that process of differentiation. So you kind of need to think in reverse a little bit when you find the antiderivative. So recall what an inverse operation is. This is not an inverse function like we saw in pre-calculus. Inverse operation, for example, the inverse of addition is subtraction. The inverse of multiplication is division. It's undoing. So the inverse of differentiation is antidifferentiation. But remember, we're not talking about inverse functions themselves. So here's a formal definition. A function capital F is called an antiderivative of lowercase f on an interval if the derivative capital F prime of x is equal to lowercase f for all values of x in that interval. So in other words, given a function that's the derivative of another function, we're going to find that other function. And we'll look at what the meaning behind the antiderivative is in chapter 5. So let's start with the power rule and polynomials. So let's look at this function, f of x equals x squared plus 1. How do we find capital F so that the derivative of capital F is equal to this? So let's think about how we would undo finding the derivative. So for a power function, the power rule tells us to find the derivative, you multiply by the power, and then you subtract 1 from the power. So the inverse process would be the inverse operations of each of those in reverse order. So we're going to first add 1 to the power and then divide the coefficient by this new power. So the antiderivative of x to the n is going to be x to the n plus 1 over n plus 1. For example, if I apply the inverse process to lowercase f here, so I'm going to add 1 to the power of 2, and remember this 1 is actually x to the 0 power. So I'm going to add 1 to the power of x to the 0 power, and so far this is what I have. Then I'm going to divide by my new coefficient. So this would be x cubed over 3 plus x to the first over 1. So this is an example of applying this inverse process to these individual power functions that make up this polynomial. So let's check it. So if that's the antiderivative, that means when I take the derivative of this thing, I'm going to get x squared plus 1. So if we apply the power rule, we take the derivative of this, we do get x squared plus 1. But there's a catch. So this guy's derivative is going to be x squared plus 1 as well. X cubed over 3 plus x plus 2 also works, right? So anytime you add a constant, that function's going to work as well. So we represent that fact by saying the antiderivative is x cubed over 3 plus x plus c, where c is any constant. So we call that an arbitrary constant. So c can be anything, and the derivative of this function is going to be x squared plus 1. And if you think about why, it's because if you move a function, when you add a constant to the end of a function, you're doing a vertical translation, right? And you're moving that graph up and down. But you're not changing the shape of the graph at all. You're just moving it up and down. And remember that the derivative gives you the slope of the tangent line. So here's that x squared plus 1. It's giving me the slope of the tangent line, which describes the shape of the graph. That's really the whole point of the derivative. The shape of this graph doesn't change as I move it up and down. So that's why when I find this antiderivative, I'm actually finding like a whole bunch of functions, because the c can be anything, any constant. So for example, here's a family of antiderivatives of the function x squared. So if I reverse the process of finding the derivative for the power rule, it'd be x cubed over 3, and I'm adding these different integers. You can see how the shape is the same, it's just translated up and down. So the derivative is going to be the same for each of these functions. So this is an example, this is called the general antiderivative. So when you tack on that plus c at the end of that function that you get when you apply the inverse process of differentiation, that's called a general antiderivative. So when you're asked to find the most general antiderivative, that means that you need to add that what's called the arbitrary constant c. So here's another example you'll see in the homework. Find the most general antiderivative of f of x. So we're going to apply that power rule in reverse, which takes practice to do. This is not the type of thing you want to hurry through because it's easy to get confused and reverse the reverse processes. So we're going to add 1 to this power of 3, which gives me power of 4, and then divide by 4. Add 1 to the power of 2, which gives me a power of 3, divide by 3. Add 1 to the power of x here, which is just 1. So I get 2, divide by 2, and then I tack on that arbitrary constant, and this is the simplified version. And we can check it by taking the derivative of this. When you take the derivative, that c goes away, and that's the derivative.